Chasing love.
Yeah, you can ask the definition.
Yes.
Yes.
Wrong.
Okay. So this comes back to what I explained last time, that if you want it to work in that formula that I gave you, right? You must first put that force as a what? You must put that force in what? As F at x. So F at x, it is compensating for this parallel that they are talking about. Right? So you must first calculate the F at x of the force if the force is acting at an angle, like I explained that time. You remember?
So many other things that are the definition. Explain that like putting the definition that.
Okay, it's fine. You can use that, right? Right? So let's go on to today's lesson, right? So today we are dealing with energy. With energy, right? So what did I explain in grade about grade 10 work? I explained something about grade 10 work, right? What did I explain? In grade 10 work, what did I explain? In grade 10 work, I explained that the total mechanical energy of an isolated system remains what? Conserved. Or it is, yeah, it remains constant or it is conserved, right? So it means that our EM initial should be equal to EM final, right? This is grade 10 work, right? So what does it mean? It means that EK initial plus EP initial is equal to EK final plus EP final, right? And I said this was only working if we were having what? Gravitational force only that is acting on the object, right? So the only force that is acting here it is Fg, right? So Fg was the only force that was acting here when we're having this. Can you see that? So it means that we're not having what? We're not having frictional force, we're not having applied force, right? So those the forces that I mentioned here, they are called what? Non-conservative forces, right? So what are non-conservative forces? What are non-conservative forces? Can you try to explain what are non-conservative forces? Yes, it's more like that. Can you try to explain it? Non-conservative forces, what are they? So non-conservative forces are the forces which, when they are acting on objects, the mechanical energy is not conserved, right? So when these forces, which when they're acting on objects, the mechanical energy is not conserved, right? So it will mean that EM initial is not equal to EM final. Does this make sense? So EM initial is not equal to EM final. This is the non-conservative forces. So which leaves that gravitational force is the only conservative force. So this is a conservative force, right? Gravitational force is a conservative force. So what does it mean about gravitational force? The mechanical energy when gravitational force is the only force acting on object is conserved. The mechanical energy is now conserved. That's when we had EM initial was equals to EM final. Right? So it means that EK plus EP. So EK plus EP, these ones, they give us what? EM, right? So EM initial, it is EK initial plus EP initial, right? So it means that if we are having an object, let's say here, right? Right? Let's say this object is here at A, right? And this object is moving to point B like this, right? So the movement of object from point A to point B, it is conserved when we are having what? When we are having only gravitational force acting on this object, right? So it means that if we're talking about in terms of this, it means that this was minus work done by non-conservative force, right? So it means that now we are talking about the work done when there's no what? Non-conservative force. And we said non-conservative forces are forces that include force applied, frictional force, and all those external forces, right? So I said here we're talking about frictional force applied, right? So here I say if the object is moving from point A to point B, and when we are having this situation minus work done by non-conservative force, it means that the mechanical energy is what? Conserved, right? When we are having a situation when we are not having this. So it means that the mechanical energy is what? Is conserved. So here we are saying minus work done by non-conservative forces. In other words, I'm saying that minus 0 because we don't have the work done by what? Non-conservative force, right? Is it making sense? Is it making sense? So now let's try to include the work done by a non-conservative force. So here we said minus work done by non-conservative force, which was 0 because there was only gravitational force that was acting on the object, right? So now let's have this. We said EK initial plus EP initial is equal to EK final plus EP final, and we said what? Minus the work done by what? Non-conservative force. Conservative force, right? So it means that here initially we having what? We didn't have this because this was a what? A closed system. This was a what? Closed system. Which means that only gravitational force is acting on this object, right? But now we are having minus work done by non-conservative force. So now we are talking about when we are having a what? Non-conservative force. So it means that this process that happens here, right? It is constant when you subtract what? This, right? So now we are including this, that we are having a non-conservative force. So we want to see what happens if we are having a non-conservative force, right? Right? So this is what I want to say. We can check this side and check this side, right? So it means that this is coming this side, right? So when it comes this side, it becomes what? Positive. So work done by a non-conservative force should be equal to EK final, right? Minus, this is going that side. It is EK initial plus EP final. And this one going that side, it will be what? EP initial, right? Negative EP initial, right? But if we check these things here that we are having here, how can we name these things? It is a change in kinetic energy. Can you see that? Because final minus initial, it is a change in something, right? So this work done by a non-conservative force should be equal to what? Change in EK, right? Plus, what about this? This is also change in potential energy, right? So this is change in EP. So this leaves our formula like this now. right? So the work done by a non-conservative force is equal to the change in kinetic energy plus the change in potential energy, right? So we can also put that in a definition, or we can put that in words, right? So this is work done by a work done by non-conservative forces is equal to the change in kinetic energy and the change in potential energy. Or we can say it is equal to the sum of, right? It is equal to the sum of the change in kinetic energy and potential energy. Can you see that? Can you see that? So now, how many formulas have we talked about so far about energy? We talked about 3 formulas so far. And those formulas, they're the ones that are what? More like complicated to understand when you are dealing with work, energy, and power, right? Most people, they find these formulas difficult. But I'll try to explain these formulas so that you won't have a problem with these formulas. There are 3 formulas that we talked about so far, right? Including the last session that we had, right? So what are those formulas that we talked about? There are 3, right? And today I'll just end on these 3 types of formulas, right? And I'll just try to explain them as hard as I can, right? So that you won't have problems with them, right? First thing, at our last session, we talked about the work energy theorem. Do you remember? The work energy theorem, right? Work energy theorem. What does it say? It says that the work net done on an object is equal to the change in EK. Do you remember that? Do you remember that? We talked about it in our last session, that the work net done on an object is equal to the change in the object's kinetic energy. So where does this formula work? So mostly they will tell you that use the work energy theorem. So this is the work energy theorem, right? It says that the work net is equal to the change in EK, right? So what do we mean by work net? We mean that the work done by what? All forces, right? So it means that here we are adding the work done by Fg plus the work done by frictional force by the work done by what? Force applied, and so on, depending on how many forces we have, right? So here we are not excluding any force. Can you see that? So we are saying the work done by all the forces is equal to the change in the object's kinetic energy. Can you see that? Can you see that? This is understandable, right? So it means that now we are adding all the forces that are happening on the object. For example, if we are having something like this object moved from point A to point B, right? So this force, this object is having force applied, right? And there's what? Frictional force, and at the same time there's what? Gravitational force. And in this case, where is Fg acting? Downwards, and it is opposing motion, right? So it means that our work net is equal to the change in the object's kinetic energy. Here the object was having initial kinetic energy, and then to have the final kinetic energy, right? So it will mean that work done by gravity plus work done by frictional force plus work done by force applied should be equal to the change in this object's kinetic energy, right? So which one, what do we do? You know how to do it, like we explained last time in terms of how we can do this, right? So it means that we can add all the forces that are acting on this object, right? F net, it is the sum of all the forces acting on the object. Although we have negative in the formulas depending on the direction where these forces are going, but we say we add them, right? That is F net. We add all the forces acting on an object. So according to this, it will mean that force done by what? By applied force, right? Plus minus force by what? By frictional force, because frictional force will be going in the opposite direction, right? Plus negative force done by Fg at x, right? Because it is going in the what? Opposite direction, right? So all these multiplied by changing x should give us what? The work net. And we equate it to what? To the change in the object's kinetic energy, right? So I said this formula, we use it when we are adding all the forces, be it gravitational force and be it the work done by what? Non-conservative forces. Here, frictional force and force applied, they are what? Non-conservative forces, right? Let's move to the second formula, which is this formula, which I said this is the Gretchen formula, right? This Gretchen formula, we said this only works when we are having what? Gravitational force only. There are no any other forces that are acting here, right? That's when mechanical energy initially is equal to mechanical energy final. So it means that here we only have what? Gravitational force. And the last formula, it is this one. Work done by what? Non-conservative force. It's equal to changing EK plus changing EP, right? So this formula, even though we are having gravitational force acting on an object, we don't include it when we are working it, right? We only include non-conservative force. So which ones are non-conservative forces? Maybe if you are dealing with this question. How many non-conservative forces are we having there? 2, right? Which is frictional force and force applied, right? So it means that here we are going to have force applied, right? Minus minus frictional force, right? All this inside a bracket multiplied by the what? Changing x should be equal to what? Changing EK plus changing EP. Can you see that? So it means that here we are only including the what? Non-conservative forces. Can you see that? Can you see that? Is it making sense? Is it making sense? It's not. Negative FF. Where are you lost? So I said, how do you know that they are non-conservative force if they are not what? Fg. Right? Fg is the only what? Conservative force that we deal with, right? So the other forces that they will tell you that frictional force or force applied, those are what? The non-conservative force. Why? Because the mechanical energy is not conserved. Is it making sense? So it means that these 3 formulas are the ones that make students hard to understand. The work energy theorem, this the law of conservation of mechanical energy, and the work done by non-conservative force, right? So how can you know which formula to use? You can know which formula to use by knowing what you are looking for, right? By knowing what you are looking for. And the tricky part is that sometimes they just tell you that use the work energy theorem. So if they tell you to use the work energy theorem, you don't decide what to use, you just use this one. And if they tell you that this situation, it was a smooth surface and there was no any external force, and they say use the energy theorems to, or the energy equations to calculate, you can choose which one to use. Mostly you can use this one, because this one, there's no what? There's no external forces, there's only gravitational force. And if they tell you that there's frictional force and there's what? Force applied. Or if they tell you that there's frictional force only, right? It's either you can use this formula or this one, right? This one doesn't matter what is happening, right? It works everywhere. Right?
So let me see other
right? Yes. So this is more like a standard formula that works everywhere, right? You can include all the forces.
We are telling you.
To use work net here.
Ako ka maka-work energy term.
And one by X.
Yeah.
What are you going to change in
Kinetic
energy?
Yes.
Apa na change in kinetic energy?
Yes.
Dengan dengan jelas substitusi dengan net.
Yeah.
Yeah.
No. Why? Because this one is using all the what? Forces, right? And this one is not. Right?
So bayar apa no?
Non-conservative forces, yes. So you just know that what are non-conservative forces? That doesn't conserve the what? The mechanical energy, right? Okay, let's try to search for an example. So we're having this situation here. So at this situation, what is happening? This is what is happening, right? We are having initial velocity of this object here is 1.25 meters per second, right? And this object is moving down this slope, right? To get to point Q. It is moving from point P to point Q, right? This object is only having frictional force that is being applied from here to here, right? So this that there's no applied force, right? So now we are just going to try to find the final velocity at this point, right? We're just going to try to find the VF at this point using either the work energy theorem, or we can use the work done by non-conservative force, right? So let's try to see. So firstly, let's use the what? The work energy theorem, right? So first thing first, let's draw a free body diagram showing what's happening here, right? So we're having this situation, and we're having this object having which force? The normal force, and we're having which force? The frictional force, and we're having what? Fg, right? And this Fg will give us Fg at x, right? So it means that our Fg at x is more like inverted, like this. This is our Fg at x, right? So they said this object is 120 kg, and this is the frictional force, right? Right?
Yeah.
So let's try to use the work energy theorem, and then we'll try to use the what? The work done by non-conservative force, right? So let's start. The work energy theorem says that work net is equal to changing EK, right? So this is F net multiplied by what? Changing X is equals to half mv squared final minus half mv squared initial, right?
Yeah.
On our F net, how many forces are we talking about? We're talking about frictional force and Fg at X, right? So this is Fg at X plus minus frictional force. Why did we say Fg at X minus? Because now Fg at X is working with the what? With where the object is going, right? So this is a positive force, and this will be a negative force. Does it make sense?
Yeah.
Multiply by what? Changing X should be equals to half mv squared final minus half mv squared initial, right? So what is our Fg at X? What is Fg at X? You know that Fg at X, we said this angle was 30 degrees, right? So Fg at X is equals to what? No, let's not put the angle. What is Fg at X? What is Fg at X? It is mass gravitational acceleration sine of theta, right? So what is Fg at X? It will be equals to what is the mass? 120, gravitational acceleration 9.8. And what about the angle? Sine of theta. No. So here, what is sine theta? You know that sine of theta is equal to what? Opposite over hypotenuse, right? So this is sine of theta because what is the opposite? 1.5 over 10. Right? So we substitute 1.5 over 10 here, right? Instead of writing sine theta, right? So this is 1.5 over 10. Yes, you can put this because sine theta is equal to opposite over hypotenuse, which is opposite which is 1.5 and the hypotenuse which is 10. So what are we going to have is f jet x? What are we having? 176,4 like this. Okay, Newton, right? So it means that here we're going to say 176,4 plus the frictional force is what? 50, right? Right? And then what is our change in x? 10 meters, right? This distance is 10 meters, right? Will be equals to half, what is the mass? 120, velocity final, you are looking for it, right? Minus half of 120, velocity initial, 1.25. So here what are we going to have inside this bracket? 176,4 minus 50 is 126,4, right?
Yeah, times 10.
Multiply by 10 to give us what? 1, 2, 6, 4, right? B equals to half of this is 60, 3 squared final, right? Minus 60 multiplied by 1,25 is what? 60 multiplied by 1,25. It is 75, right? And then we bring 75, this side it will add. So 1264 plus 75. 1,339, right? And then we divide by 60. 22,32, and then we square root 4,72 meters per second. This was our final velocity there, right? Let's try to use the work done by non-conservative force to see if we can get the same answer, right? So we said work done by non-conservative force is equal to change in EK plus change in EP, right? So this is frictional force because we are only having frictional force, right? Multiply by what? Change in X, right? Should be equal to what? Half mv squared final minus half mv squared initial, right? Plus mg h final minus mg h initial, right? So what is the frictional force that we are having? 50, but it is going in the opposite direction, so put what? Negative 50, be multiplied by what? By 10. Okay, be multiplied by 10 is equals to half, what is the mass? 120, and the velocity squared final, we are looking for it, right? Minus half 120, and initial velocity was 1,25, right? Plus, what is the mg final? So the final, it is here, which is 0, right? Because the height here is 0, so this becomes what? 0, right? So we just say minus, what is the mass? 120, rotational acceleration, 9.8, and the height being what? 1.5, right? So let's see, this one will give us negative 500 b equals to 60 b squared final, and this one gave us what? 75, right?
Yeah.
Is it? So this is 75, right? You got what? 75, right? What about here? 120 multiplied by 9.8 multiplied by 1.5. My 8 multiplied by 1.5. 16.
Yeah. The 16344.
Hey, what's happening? Can you do it again?
Oh, whole 9, little 9 chef.
Yeah, 9.8.
Yeah, only 1764.
1764. Does it have a comma? Okay. And then it means that you are bringing this now, this side, there will be positive, right? So it will be 60 b squared final is equals to negative 500 plus 75 plus 1764. What do we have?
1369.
So 60 b squared final is equals to 1339 divided by 60, 22,32, and square root 4,72 meters per second. So this is equals to that. Yes. So this is when you are using the what? Work done by non-conservative force, and this is when you are using the work net. Did you see the difference? Here on work done by non-conservative force, we only included the what? Non-conservative force. And here we included the what? FG as well. Can you see? So this is how we can work this. But as long as they say use the work energy theorem, we use this one. But if they don't say use any that you want, yes. What? Yes. Especially divided by 60. Yeah, and then square root. Yes. Sorry about that. So this is the square root of sides. To get our answer, right? Is it given? So this is how we can work using this formula. So this formula works when you are using what? Non-conservative forces. And this one works when you are using what? All the forces. Can you see that? So it means that also here, if we are having applied force, so we're gonna say what? Force applied plus minus frictional force. Can you see that? If we're having force applied. Can you see that? No, we didn't include it anyway. Why? Because it is perpendicular to the plane. We didn't include it, right? Is it making sense?
Yeah.
With practice it will make sense, right? You just have to put it in practice. I think on work done by non-conservative forces, we can end here. And then it means that our next lesson will be about what?
So many.
Yes. It's FGX when? This one. Yes, you can do that. Because sin theta is equals to what? Opposite over hypotenuse, right? So it means that if you're having your thing like this, and you're having your eye here and your opposite here and your hypotenuse, right? So instead of first finding the angle, you can just say sin theta is equals to opposite over hypotenuse, and you just take this and substitute here, right? Other than first finding the angle and then you put sign of the angle, you can still just use this, right? Yes, if you use it, you found the angle to be 13. You said you found the angle to be 13. Yeah. No, it's not 30. So it means that the angle here it is opposite of hypotenuse, so it is sine of what? 1.5 over 10. It means that our theta will go to sine and then 1.5 over 10. What do we get?
8,6.
It's what?
8,63.
8,63. So even if you substitute sine 8,63, we're gonna get the same answer. Right? Yes. Any more questions that you have? Do you have any questions? Any question? So yes. Gravitational force like FG. No, not really. So as I explained last time, I said FG depends on the motion of the object. Itself FG is always acting downwards, right? So if we are having a slope like this, FG at x is acting downwards. This is our FG at x, right? Now, if the object is going up, it means that FG at x has a negative. But if the object is going down, object takes you have what? Yes. Alright? Yes. Sometimes.